Hello friend, I Nagin Patel and my team member Digvijay Pund and Ashwin Ande presenting 3-bit serial input serial output shift register. So first let's understand what is a register. A register is a set of flip-flop which is used to store multiple binary bits. Number of bits stored is equals to the number of flip-flop used. Now come to the shift register. As its name suggests, it is used to shift stored binary bits to the left or right. Now as per our topic, serial input serial output shift register, in which data is inputted serially as well as output is taken serially. For 3-bit SISO, we need 3 JK flip-flop. For that, we need 3 IC of 7473 and 1 IC of 7473 contain 2 JK flip-flop. And for our convenience, we have taken 1 JK flip-flop for 1 IC. And for converting JK flip-flop to D flip-flop, we have taken 1 NOT gate IC, that is 7406. Now moving on to the circuit, since the clock is negative as triggered, we are giving the negative clock to each JK flip-flop at pin number 1. Here we have given negative clock to each IC at pin number 1. Output of the first flip-flop, that is from pin number 12, is fed into the second flip-flop for as J, and its complement is given to K. And similarly for the third flip-flop, its output wire is given at pin number 12. Here we have the output wire.
Here initially we are taking the outputs QA equals to 0, QB equals to 0 and QC equals to 0. Here we are taking an example of input 1, 0, 1. We have taken here 3 bits because we wanted to build a 3-bit SISO shift register. Initially we are inputting 1 to the data input. 1 will come here. During the first negative clock, this one will be the input for the first JK flip-flop. So as J equals to 1 and its complement K equals to 0, the output QA will turn from 0 to 1. At that same clock, the input from QA will be given to the J. So here it will be 0 and its complement will here 0 and it will be fed into K. So QB will remain 0 as J equals to 0, K equals to 1 is 0. So QB will remain 0 and QC will similarly remain 0. For the next clock, for the next negative clock, we will input 0. We will input 0 at the data line. So the input will be 0 and its complement K is equal to 1. So for 0, J equals to 0 and K equals to 1, output is equals to 0. So QA will turn out to be 0 and this previous one will be fed to J input. So J equals to 1, K equals to 0. J equals to 1, K equals to 0 will give you the output of 1. So 1 will be passed from here to here. So QB will turn out to be 1 and previous QB equals to 0 will be the input for J. So J equals to 1, K equals to 0, J equals to 0, K equals to 1 will turn out to be 0. So QC will be 0. For the next negative clock, we will pass 1 to the data input. So here we will get 1. For the previous 0, for 1, J equals to 1, K equals to 0. 1 will be shifted from here to here. So 0 will turn out to be 1. For previous QA equals to 0, as the previous QA was 0, so J equals to 0 and K equals to 1. So we will get QB equals to 0. Now for previous QB equals to 1, so K equals to 0, so QC will be 1. So we will get the output as 1 for the very first time in the circuit. Now to get the required output, we will fed any type of the input for the next 2 low clocks so that we can get a required 101 output. Now let's implement this circuit onto the breadboard. Here I am giving the clock from this switch and this is used to give the input. We are giving the input of 101. So at the first low clock I am giving the input as 1. This input 1 is stored in the first flip-flop. Now we have to give 0. So for the next low clock I am giving the input as 0. So 0 is given. So this 0 is stored in this flip-flop, and the previous one which was stored in this flip-flop is shifted to next flip-flop. Now we are going to give the third input, which is also 1. So at the next low clock, I am giving the input as 1. Now this input 1 is given, so this 1 is stored in this flip-flop, and the previous one 0 which was stored in this flip-flop is given to this, and the 1 which was stored in this flip-flop is shifted to the next flip-flop. So 1 was shifted to this flip-flop, and we have taken the output from the pin number 12, so we can see the 1 stored in this flip-flop at the output. So 1 which we had given at the very first low clock is displayed over here. So to get the required output, that is 101, we can give any two next inputs or whatever we want. So here I am giving the inputs as 00, so that we can get our required output. For the next, I am giving it out to be 0, so it has turned out to be 0, and for the very next also I am giving it as 0. So we can see that when I give next two low counts, the output turned out to be was 101.